So in 1976, in this paper, Hénon introduced the two-parameter family of smooth diffeomorphisms. I denote them here FAB, given by this formula to show that the numerical experiments for A equals 1.4 and B equals 0.3 indicate the existence of an attractor, strange attractor. So from that moment, this family of maps somehow turned out to be one of the most studied family of maps in dynamical systems. Last weekend I came from Banff. There was a workshop there last week, and the whole workshop was devoted to Hénon maps. And it's really a wide area of research. So there are talks about dynamics of aspects of dynamics of real Hénon maps, of complex Hénon maps, arithmetic aspects, transcendental aspects, and so on. So really huge area of research. I'm interested in real Hénon maps, which means two real variables, two real parameters. And I am interested in the set of parameters where Hénon maps exhibit the strange attractor. So the first proof, mathematical rigorous proof of the existence of the Hénon strange attractor was given in this paper, this remarkable paper by Benedicks and Carleson in 1991. They proved that if B is greater than 0 and small, then for a positive measure of values A close to 2, the corresponding Hénon map FAB exhibits a strange attractor. After that breakthrough, several generalizations appeared. For example, in 1993, Mora and Viana proved existence of strange attractor for so-called Hénon-like maps. And for Jan and my result, the most important paper is the one that appeared in 2001 by Wang and Young. In this paper, they gave conditions for strongly dissipative maps that guarantee the existence of strange attractors. And they proved a lot of results in this paper, many statistical properties associated with chaos. They also developed symbolic coding of orbits. But what is the most important for our work is that for the attractors in this class, they developed the geometry of fractal critical sets. So what are critical points that is critical set? I will try to explain a little bit later on. But now, let me say just that the result hold for the Hénon family of maps for a positive measure set of parameters A and B, such that B is very small and A is arbitrarily close to A star, where A star is any number between 1.5 and 2, such that the corresponding quadratic map Ka star is a Misurevich map. And to be Misurevich map, this means that critical point here is 0. So if you consider forward orbit of the critical point, then all points in this orbit, in forward orbits, are bounded away from 0, from the critical point. So we call this set of parameters the Wang-Young parameter set, and we denote by Wy the set of Wang-Young's parameters when B is greater than 0. So Jacobian is negative B. So B greater than 0 means that the corresponding Hénon map is orientation reversing. And note also that earlier mentioned Benedicks-Carleson result is a version of the case for A star equals 2 and B is greater than 0. And so let me emphasize that these Wang-Young's parameters, for these Wang parameters, the critical set is the sole source of non-hyperbolicity in the systems. This means that this critical set, whatever it is, I'll explain a little bit later on. So if you take any point in the attractor and consider its orbit, and if its orbit is, so for every epsilon, if you take points such that the whole orbit, all points of orbits are bounded away epsilon from the critical set, then every point in this orbit is hyperbolic point. So there is a splitting at this point. So only critical set doesn't have this property. So from now on, for simplicity, let us denote by capital F a Hénon map, and we assume that parameters are in the set WY, and let us denote by lambda F the strange attractor of F. So Hénon map F has two fixed points. One is in the first quadrant, and we denote it by X, and the other is in the third quadrant, and we denote it by Y. And we denote the unstable manifold of X by WU. And in this figure on the left, you can see in blue a piece, my sketch of a piece of an unstable manifold of the fixed point X. And we denote the stable manifold of the fixed point X by WS. And here is a very short piece in red of stable manifold of X. And in the other figure to the right is a computer simulation. In red is stable manifold of the fixed point X. And in black is the Hénon attractor, strange attractor. So maybe here I could try to explain a little bit critical points. So some of critical points are marked here. So roughly speaking, critical points are those points which maps to these folds. This means that if you take for example, this is a critical point, this one up here. And if you take a unit vector in vertical direction, 0, 1, at the critical point, then, and if you apply derivative of f to the n for every n, it is expanding because it goes in the unstable direction and stays in the unstable direction all the time. And if you take a unit tangent at this critical point, if you take unit vector in tangent, which is tangent to the unstable manifold at that critical point, then it is mapped by derivative to the stable direction. And when you apply derivative of f to the n for all n, it stays in the stable direction. So this critical set is a Cantor set. So, in my talk, I will focus on the pruning from conjecture, on the solution of the pruning from conjecture, and at the end, I hope I will have enough time to say a few words about application of this solution of pruning from conjecture to the classification of the Hénon maps within this parameter set. So, as it is well known that Milnor-Thurston kneading theory in one-dimensional dynamics is very, very powerful tool. So, central object of the Milnor-Thurston kneading theory is itinerary for unimodal maps is on an interval is the kneading sequence. And the kneading sequence is itinerary of the critical value, not of the critical point, but of the critical value. And this symbol sequence of two symbols, characterize the set of all possible itineraries of the unimodal maps with negative Schwarzian derivative and without periodic attractors. Moreover, the kneading sequence is an invariant of the topological conjugacy classes of such unimodal maps, and moreover, it is a key tool in proving monotonicity and continuity and monotonicity of the topological entropy for quadratic family, and it's really very powerful tool, very useful. And the idea to develop such theory, symbolic dynamics for two-dimensional dynamics is quite old. In 1988, in this paper here, Cvitanovi, Gunaratne, and Procacci proposed a symbolic dynamics model for what they called Hénon type maps. That is, for maps of the plane that fold the plane back into itself exactly once, and they especially address the case of the Hénon and lossy maps. They stated that every allowed orbit has a unique binary label and that a binary tree that contains all allowed orbits is not complete. Since these allowed orbits are pruned from it, so they coined this term pruned, and they called a boundary that separates the allowed and the forbidden orbits a pruning front. And in this paper, they write, here is a citation, a pruning front arises from the fact that the two-dimensional attractor is not a single curve, but is multi-sheeted. There is no single maximal point, as in the one-dimensional case. Each sheet defines a locally highest allowed itinerary. We conjecture that the pruning front specifies the allowed symbolic dynamics fully. There are no orbits which are pruned out by other mechanism. All the other disallowed regions of the symbol plane are obtained by backward and forward iterations of the primary prune package. And this conjecture is today known as the pruning front conjecture, and it has received a lot of attention in the last 35 years. So Jan and my approach to the pruning front conjecture is motivated in part by the piecewise affine case of the lossy maps. I really will not mention, there are a lot of results and papers about pruning front conjecture. I will not here, I apologize, I will not mention any result, just one, because it is related to lossy maps. And so in this paper, from 1997, Yuta Kaishi proved the pruning front conjecture for the lossy maps. But to prove this conjecture, he used this formula for the lossy maps. And this formula is very specific, so it's piecewise affine family of maps. And in 2016, Michal Misurevic and I developed the kneading theory for the lossy maps. And in this work, Misurevic and I avoid this use of this formula, having various applications in mind. And that allowed Jan Boroński and me to follow the main idea in the lossy case to prove the pruning front conjecture for the Hénon maps and to develop the kneading theory. But as we all know, there is a big difference between the lossy maps and the Hénon maps. So we have to develop some new methods and tools to address these differences. One of the main distinctions in developing symbolic dynamics for the Hénon and lossy maps is as follows. So the idea to use y-axis to partition a plane into the right half plane and the left half plane is old and natural, and it is used for a long time for the lossy maps. But the y-axis doesn't play any special role for the Hénon maps. So Cvitanovi notice that a partition of the plane by the y-axis does not determine the periodic points uniquely. Numerically, it appears that a line joining the homoclinic tangencies does in fact partition the plane as needed. And we conjecture that this line partitions space so that the unstable periodic points are uniquely described by symbolic sequence. But the first question is existence of such a line or curve or whatever. And even in the Benedicks-Carleson paper, they say that one might, for example, believe, although this is doubtful, that this critical set script C is located on a smooth curve cutting through the unstable manifold of the fixed point X. We can, however, only prove this for C1/2 curve, and this is based on the fact that WU never intersects itself. But Jan couldn't find any proof of such this statement. So we first had to prove the existence of such a curve, which contains all critical points. And we proved that. I will state the theorem. And so we denoted this, we proved that there exists an arc. So we denoted that arc by script K, and we call it the critical locus. So let script C be the Cantor set of all critical points of F. But not all critical points are equally important for us. For us, the most important critical points are those that belong to the unstable manifold of the fixed point. And therefore, we give them the special name, we call them the basic critical points, and we denote the set of all basic critical points by this letter. This is fractional C or Gothic C, I will call it frac C. So I have frac C, script C, but I think we will know which one is what. Okay, so the set of basic critical points is countable, so we can index them. And we do this in the following way. Mm-hmm. Yes. Okay. So let Z0 be the first basic critical point on the unstable manifold on the left of X. And now we partition unstable manifold by the real line. We parameterize the unstable manifold by the real line such that 0 parameterization is 5. I will need this parameterization later on. But for now, phi of 0 is the fixed point X, and Z0 belongs to the image of the negative part of the real line. And using this parameterization, we index the set of critical points, but in this moment is simpler to see on the picture. So this is Z0, and then we just follow the unstable manifold, and the first one is Z1, second one is Z2, and so on. If you go to the right of X and follow the unstable manifold, first one is Z-1, Z-2, Z-3, Z-4, and so on. So this is indexing. And now we call the set of all iterations of all basic critical points the basic post-critical points. And for simplicity, we denote by P to the I for a point P in the attractor, we denote P to the I iteration of the point P. This is for all I, therefore P is the same as P0. And so we proved that there exists an RK such that this RK intersection attractor is equal to the set of all critical points, and the endpoints of this arc K are Z0 and Z negative 1. So this is one green arc. And now when we have this arc, we use critical locus to partition a forward invariant disk D in green here that contains the Hénon attractor into the left and right regions as the base for the symbolic dynamics for the Hénon maps.
This arc is just continuous.
Just continuous. So in Wang-Young paper, they claim that it cannot be smooth. So the disk D is defined and denoted as in the Benedicks-Carleson paper. So the boundary consists of two pieces, two arcs. One is denoted the unstable boundary of D. Unstable boundary of D consists of a piece of unstable manifold, and the other piece of boundary is this line L. This is an artificial line which is tangent to the attractor. And so it's easy to see that D is forward invariant and contains attractor of the Hénon map. So we denote by DL the region of D that lies to the left of the critical locus, and by DR the region that lies to the right of the critical locus, and both of them contain the critical locus because we need compact sets. And we code the points of the attractor in the following way. So to point P in the attractor, we assign a bi-infinite sequence, P bar. So here is decimal dot. It shows where the zero coordinate is. Zero coordinate is on the right of decimal dot. And coordinates are Pi, Pn. Pn is minus if n iteration of P belongs to the DL. So it lies to the left of the critical locus, and Pn is plus if an iteration of P lies to the right of the critical locus. And standard notation, standard terminology, a bi-infinite symbol sequence Q bar is called admissible if there exists a point Q in the attractor such that Q bar is assigned to Q, and this sequence is called an itinerary of Q.
What do you do with the overlap?
The
Overlap?
Yes, yes. Since both components that we use for coding contains the critical locus, some points of the attractor can have more than one itinerary. So we denote the set of all admissible sequences by sigma f. It is a metrizable topological space with usual product topology. And since both this DL and DR contains boundary, intersected with attractor are compact, this space is compact, and we proved that this map phi from the symbol space to the attractor defined such that to a sequence P bar, the sequence is mapped to the point pi of P bar such that this point has itinerary P bar. This map is well defined, and this is a semi-conjugacy between the from the Hénon map to the sigma, and sigma is a sheet map on the symbol space. So first, because we start the choice of parameters is such that parameter A is such that the corresponding critical quadratic map is Misurevich map. So therefore, the consequence of that is that for every critical point Z, all forward iterations are not critical points. And moreover, because F is a homeomorphism, at least, so all backwards iterations are not critical points. So therefore, all forward and backwards iterations of critical point are not critical points. And the consequence is that if we have a point P from the attractor, it has at most 2 itineraries. And if P has 2 itineraries, they differ at only 1 coordinate. Let's say K coordinate, and in this case, PK is a critical point. PK belongs to the critical locus. And in such case, for simplicity, we write both itineraries of P as just one sequence, P bar, but on this place PK, on this coordinate PK, we put both symbols, plus and minus, to indicate that in fact we have 2 itineraries. And to be able to state our results, just a little bit more notation. So for a sequence P bar, we denote by Pn with this arrow pointing to the left infinite sequence. We start with Pn and goes to the left and call it the left tail of P bar, and the right tail of P bar is the right infinite sequence. We start with Pn and goes to the right and is denoted by Pn with this arrow pointing to the right. A finite sequence we call a word. This is tradition standard, and we denote an infinite to the right sequence which consists of all pluses. By plus to the infinity, this infinity is to the right. And if a to the left infinite sequence consists of all pluses, we denote it in this way. So now, first, we consider itineraries of points of unstable manifold of the fixed point, and we denote by sigma WU the set of all itineraries of WU. So first of all, fixed point, which is to the right of the critical locus, has itinerary which consists of all pluses, and we denote it X bar. Then WU, so this is an unstable manifold of the fixed point X. This means whichever point you take and iterate it backwards, this sequence converges to X. But this means that every itinerary of every point of unstable manifold has a left tail which consists of all pluses. So basic critical points are points on unstable manifold. And the image of the basic critical points will play a special role in our proof on the pruning from conjecture. Therefore, we give them special name, we call them turning points. So recall, in one-dimensional case, kneading sequence is the itinerary of the critical value. Now, this set F of Procacci are somehow, let's say, critical values, so images of critical points. And the itineraries we call kneading sequences. So if we have critical point Zi1, so this is the image of critical. So if we have turning point, if we have turning point Zi1, this is the image of the critical point Zi. So then its itinerary is the kneading sequence K bar I. And we denote by Prac Kf sub F the set of all kneading sequences. And we call it the kneading set of the Hénon map. And so what is important now is that first of all, the set of all kneading sequences is of course a countable set, and every kneading sequence has the following form. So here is decimal point, so which means 0 coordinate is on the right. And since turning point belongs to the alternate points lie to the right of critical locus, so K0 is plus. And then we have some right tail. Right tail we start at plus. Pre-image of the turning point is a critical point. And this critical point, therefore, here we have plus minus. And as we already have seen, there is an integer such that the left tail from that integer to the left consists of all pluses. So between this integer and this plus minus, we have a finite word. So this finite word should start with minus, because this is the, so if we start from decimal point and go to the left, this is the last minus we see, because after that to the left we see all pluses. So every kneading sequence has this form. And we prove the pruning from conjecture by proving that this critical set, this kneading set characterizes all itineraries. And the proof is given in 2 steps by 2 theorems. First, we prove that the kneading set characterizes all itineraries of points of unstable manifold of the fixed point X, and we call this WU admissibility. And since WU is invariant for F, the set of all WU admissible sequences is invariant for the shift map sigma, and this means that apart from the sequence which consists of all pluses, and we know that this sequence is WU admissible because it is the itinerary of fixed point X, we only need a way to check WU admissibility for sequences of this form. So this means that we just consider sequences which has the left tail from the decimal point to the left, which consists of all pluses, and the right tail P0 is the one which starts with minus. And first theorem says a sequence of this form with P0 is minus is WU admissible if and only if for every kneading sequence which has this form such that this finite word W is an initial part of this right tail. So for W, for the kneading sequence which has this property, we have this inequality, shift to the n plus 2 of right tail P0 is less than or equal the right tail K0, where this is standard parity lexicographical ordering. And let me compare this formula with the one-dimensional case. So if we have some unimodal map, here is critical point C, map is F, here is F of C, and then here is F2 of C. First of all, this interval between second image of the critical point and first image of the critical point is a dynamical core. So all interesting dynamics is here. I already know this interval, but I, so it is enough to consider F restricted to I. And in this case, so let K bar, this is now one-sided sequence because this is one-dimensional case. Let this be itinerary of the critical value. So this is the kneading sequence. And let P be sequence, any sequence. So this sequence is admissible if shift to the n of P is less than or equal K for every n is n. So this is the formula in the one-dimensional case. So first of all, so this formula is really very elegant, very nice, very compact, but in fact, we have here countably many requirements, because for every n, we should have this inequality. So here, again, we have countably many conditions. Moreover, here we have just one kneading sequence. So every shift we compare with this one kneading sequence. We have here similar formula, but we have countably many kneading sequences. So we need a criterion when to use which of these countably many sequences. And criterion is given here. So what it says? It says, okay, let's take first right tail P0. And if this right tail has initial power equal to some word V, where V is a word of a kneading sequence, then we take this kneading sequence and compare and make this compare in this way, if this is less than or equal K0. And then we do the shift. And then we take this sequence and look if there is some finite piece, initial piece, which is again this word of some kneading sequence. And if it is, then again we compare like that. And so we go shift by shift, and this is criterion when to use which kneading sequence. So this is somehow the same, similar. So we just have an additional criterion when to use which sequence. And now, when we know which sequences are W admissible, and since the symbolic space is equipped with the product topology, it is easy to see that the following theorem holds. So a sequence P bar is admissible in general, if and only if for every positive integer n, there is WU admissible sequence such Q bar such that P bar and Q bar agree in a central piece around decimal point of length 2n+1. Okay, and note that the kneading sequence, the kneading set frac KF is indeed the pruning front, and that these two theorems prove that all the other disallowed regions of the symbol plane are obtained by backward and forward iterations of the primary pruned region, which is the statement of the pruning front conjecture. Okay, so we have it. But if you think a little bit longer about that, we see that in one-dimensional dynamics, we have just one kneading sequence. And this one kneading sequence, this one sequence is very powerful. As I already mentioned, you can use it for everything. But the Hénon maps are maps of the plane, on the plane that fold the plane back to itself exactly once. And as such, they could be considered a two-dimensional analog of the unimodal maps of the interval. And a natural question is there such good sequence of two symbols for the Hénon maps? And the most exciting part for me is now that the answer is yes. So, and we call the sequence the folding pattern. And let me show you what is the folding pattern. So this is a notion, new notion for the Hénon maps, where the whole information about the symbolic dynamics is maximally compressed. So now we go back to our parametrization. Recall 0 is mapped to X. And now Z0 is in the image of the negative part of the X of the real line. And now we require additionally that all other integers except 0, 0 is not to X, are mapped to the union to the set of all basic critical points and basic post-critical points, which we call basic points for simplicity. So 0 is mapped to X, and in particular, -1 is mapped to Z0, and 1 is mapped to its image turning point Z01. And now we consider a bi-infinite sequence pi of k, when k goes through all integers. And this sequence contains all the information on how W is folded in the plane. So let me show you. So here, this short piece of unstable manifold of X. And this is the same short piece, the same piece of unstable manifold of X, just straightened. And here, so here is X, and then is Z01, Z01, then Z negative 1, Z negative 1, Z03, Z03, Z negative 2, and so on to the left. And now what we do, we simplify this sequence by still keeping all the information, and we simplify it in the following way. So we replace X by decimal point, and we replace each critical point, Zi, by the symbol 0, and each post-critical point, Zi to the j, by 1. So here is post-critical point 1 after decimal point, critical point 0, post-critical point 1, critical point 3, post-critical points in the row, 3 ones, and so on. And we get a sequence like this. We call this bi-infinite sequence of two symbols, zeros and 1, the folding pattern of F. And we prove that it characterizes the set of itineraries of such Hénon maps. The theorem says the set of kneading sequences and the folding pattern are equivalent. That is, given one of them, we can recover the other one. Moreover, it is an invariant of the topological conjugacy classes of the Hénon maps within the set WY. So using this, we classified the Hénon maps. And if you give me 3 minutes more, I could show you this.
For 3 minutes.
Pardon?
3 minutes.
Thank you very much. So as I said, we classify Hénon maps on their strange attractors within the parameter set WY, and our proof relies on this pruning from conjecture and on some results from 2 recent papers. One paper is this Croisier-Pujol paper from 2018. In this paper, they prove that if G is a strongly dissipative CR diffeomorphism from this to itself and R is greater than 1, then there exists a semi-conjugacy between G and a continuous map F on a compact real tree T, which induces an injective map on the set of all of non-atomic ergodic measures mu on G, and moreover, the entropies of mu and pi star of mu are the same. And this compact real tree is, in fact, a dendrite that is a locally connected continuum that contains no simple closed curve. And recently, Jan Boroński and me in this paper showed that for each Hénon-like map F, now we need just Hénon map, there exists a densely branching tree T. This T is from the Croisier-Pujol paper, such that F on its strange attractor is conjugate to the Schiff homeomorphism on the inverse limit of T. And we prove that there is no simple model. If you want to have this result, then T should be densely branched. And so, to classify Hénon maps, from these trees, we specify 2 special sets, EX and BX. So this is densely branching tree. So there are countably many branch points, and BX is the set of all branch points. But there are uncountably many endpoints. And we specify the set EX. This is a countable subset of all endpoints. This is set of special endpoints, and it is also countable. And in this lemma here, we prove that this conjugacy between the inverse limits and the Schiff map on the inverse limits and Hénon map of the attractor gives us a bijection between the orbits of turning points and elements of this set EX union BX. And that was very important. Having this, we were able to show that if we have two Hénon maps, F1 and F2, with these parameters, and if we denote by L1 and L2 the corresponding attractors, and if we denote by Rj the turning points of L1 and by Sj the turning points of lambda 2, and if we suppose that there exists a conjugacy H, capital H, between F1 and F2, then there exists an integer k such that H of Ri to the n is equal to the Si to the k plus n for every I and for every n. So this one k is for every I and for every n, which means that the orbits of turning points of lambda 1 are mapped to corresponding orbits of turning points of lambda 2. And having this, because turning point itineraries of turning points are kneading sequences, this theorem implies that two Hénon maps with parameters in Wy are conjugate on the strange attractor if and only if the set of kneading sequences coincide. And because the set of kneading sequences is equivalent to the set of this sequence folding pattern, this is if and only if the folding pattern coincide. And this is how we classified the Hénon maps. So thank you very much for these 3 minutes.
Questions? Or maybe I have one. Are there indeed Hénon maps which are conjugated on their strange attractors?
There are Hénon maps.
So here there is a criterion for telling the necessary or sufficient condition for being conjugated on their strange attractor. Are there different parameters?
That we don't know. So we don't know for which parameter we have some kneading sequences. So we cannot know, are there some equal topologically conjugate Hénon maps, or which are not topologically conjugate. But maybe what is important to mention is that this folding pattern gives us possibility to decide that infinitely many steps. So if there are two Hénon maps which are not topologically conjugate, which I suppose that all of them are not topologically conjugate, so then we can find this infinitely many steps. Because we just look at folding pattern and we see first difference, then we know they are not conjugate.
Does the folding pattern need this line or what?
Folding pattern, this is just a sequence of zeros and ones.
I know, but does it use this line construction?
It uses all critical points,
Oh, critical.
and they belong to this arc.
So to compare two by their folding patterns, you don't have to compute this arc for two different.
No,
You can just
no.
do zeros and.
So you have this, you have this symbolic dynamics, the sigma f. Do you know something about its structure? I mean, does it satisfy some kind of specification property, for instance?
About attractor?
Sorry?
About what? Specification?
Property for the symbolic dynamics that you build.
The collection of allowable examples.
No. So first of all, the only thing, so this is completely recent work. So we just started. So the only thing I know about kneading sequences is the one which is of the most right turning point should be shift maximum. And I don't know anything about others. I just know that every one to the left should be smaller in parity lexicographical ordering. And I don't know which so in one-dimensional case, you know which sequences are kneading sequences of quadratic maps. So they are shift maximal. All shift maximal could be kneading. But here we don't know anything. And so it just, everything is completely new.
So you said that if you have two maps which are not conjugate, you will know it in finite time. But if they are, you actually cannot do this, right? Because you need to check engineering.
Yes.
Thank you again.
Thank you.
So we have more 10 minutes.